Hopefully it is going to be of some interest. What I intend to do is to go over a broad set of issues and the way that we have classified these issues into different buckets, because it's more important to ask the right questions. It's a little easier to try to get the answers when you have the questions in front of you. Right? So this talk is really intended to ask the questions. It's not intended to lay out some solution which already exists. Okay? Stop me at any time you want. You don't have to wait till the end of the talk for questions. So this is the agenda for the talk today. I'll briefly go over what cloud computing and virtualization have to do with each other. Take a look at the benefits of virtualization and then start digging into the issues. That's the bigger part of the talk, which is the part 3, and then we'll just conclude very briefly. Just before we get into that, I'm actually representing a much larger group of researchers at the Computer Science Department at IIT Bombay. We call ourselves the ProVM Research Group. There are many of us. There are 3 faculty members, Puru, Varsha and myself. And these are all the current PhD students who are working with us. We have about 10 PhD students. There are 1 or 2 who are not on this. They are relatively new. And we have about 10 to 12 MTech students in the group as well, and almost 15 BTech students in the group. So it's a fairly large group, and whatever I'm going to talk about today is joint wisdom of all these people. So I'm just here, I'm lucky to be presenting it in front of you. Okay, so not sure whether you can see this very clearly, but I'll explain it. I just did a Google Trends yesterday evening on the internet for 2 terms. The term in the red is just a term called cloud computing, and the term in blue is a term called virtualization. What Google Trends gives you, how many people here have done Google Trends earlier? It's all big data. It's part of the big data. So this is just showing the number of searches taking place for these terms, right? And the relative change from 2004 to 2014. If you take a look at the last 10 years, how many people have searched for these terms worldwide, and it also gives it by the top 10 or top few countries from where the search terms are coming, and India is number 1, as you can see. More people in India are Googling for either cloud computing or virtualization than anywhere else in the world. Right, the second country being Singapore. So there is a lot of interest in India in this topic at this point in time. So what is cloud computing? I just put up a definition that NIST has come up with. It's a fairly accurate concept of what we would call utility computing. The concept of a utility being that there is some shared resource out there, such as an electricity power plant, for example, or a water purification plant, or what have you. So there is a shared pool of computing resources as far as we are concerned. So there has to be something that is shared by multiple people, and for us the computing resources are shared. And then you can access these computing resources remotely over a network. Right? So you don't actually have to have the computing resources here in this college, in this university, wherever. So all the universities in Kerala, for example, may be connected to a Kerala cloud. Or in India there could be an academic cloud, and so on and so forth. Right? So it is access over the network, shared pool of computing resources. And third, important point being that they can be very precisely provisioned to the needs of the user. So for example, if you say I want a computer that has 2.16 gigahertz cores, and I want this to have about 8 gig of RAM, and I want to have this I/O bandwidth for this computer, then I'll be able to get that. Right, so it's like going to a shop and saying I want 300 grams of something, and they will be able to put it into a bag and give it to you, right? So the same concept but with computers, which is rather novel because earlier you had to buy computers in the fixed things that they came with. The concept that I could have a 1-core 4 gig computer today and I could have a 16-core 64 gig computer tomorrow with the same machine is somewhat novel. So that it can be precisely provisioned. And it can also be rapidly provisioned. In the sense it can be done online. Right? So you don't need a human being who will receive a request for such a computer and provision it in time and give it back to you. So this is automatically done by software behind the scenes. Right? So this is the definition of cloud computing. There are other definitions out there, but NIST is an accepted notion. So the basic concept behind the scenes being that this is computing as a utility being that there is some shared resource that is being consumed by many people out there, and the cost of the resource is being split amongst the multiple people consuming it, right? So the management of the resource, the updating of the resource, the upgrades, the patches, whatever it is that you have to put, you are not worried about all of that stuff, right? So this concept of sharing is not very new, right? We've seen this early models had this concept of what we call time sharing. Time shared computers, not sure how many of you here were exposed to that, but back when I went to college, we had this concept of a time shared computer. There was one big DEC PDP-10 or some such machine, and everybody would get time slots on this machine, right? It's not that the computer was always there for you, no. You only got a half an hour or a 45-minute time slot on this machine, and you could go do your work there. Typically, you had a card deck that you had to write your program onto the card deck, and this card deck would be fed into the computer, and the computer would run the program. And if there was an error, you went back, prepared another card deck, and came in the next time slot, which was, by today's standards, a ridiculous way of doing it. Right? But that's what it was early days. So this is an example of an ATM machine, which is time shared even today. Right? Two people cannot use the ATM at the same time. There's only one person who can use it at a time. So in that sense, it is time shared. You get a time slot on the ATM. After that, we moved toward personal computing models. So these time shared computers, these big computers made way for smaller, fairly powerful machines which would sit on your desk or in the palm of your hand, as the case may be, and it could do a fair bit of things. A fair bit of computing. There is no sharing concept here at all, but this was somewhat of a management headache. So if you ever owned a Windows PC at home, you know what I'm talking about, right? Every 2 days there is some patch that Windows releases, some security patch, viruses infect your machine all the time. There is some software that has to be added, configured. It's quite a pain to manage these personal devices. What would be nice would be to have a no management headache kind of a computer, right? That you can use on demand and let go. That's the concept, right? And this also does not scale. If you buy a PC, then you are stuck with the configuration of that PC. If you want a bigger PC tomorrow, then you have to sell this or get rid of it and get a new PC, right? It's not that today I have a certain computing need and tomorrow I have a different computing need, and I scale my resources appropriately trained tomorrow. That doesn't happen with these devices because they're owned by you, they're managed by you, and once you bought it, you keep it, right? It's not very mobile in general. So the third model that we look at, which is somewhat central to the concept of cloud computing, is the concept of space shared computing models. Right? Space shared is that this is an example of a large office where this space is shared by dividing it into small cubicles, and everybody occupies 10 square foot of place inside a hall that may be thousands of square foot large. And everybody is out there working at exactly the same time. So there's no time sharing of this concept, in this concept, right? So that's the concept we're talking about, but applied to computing, right? You have one big computer and you're used to this as well to a certain extent, particularly in your college campuses and so on, where you have one large computer which we call a server, and many people can log into the server and work simultaneously, right? So this is space sharing in a way because you're using a tiny bit to the computer when others are using bits of the computer as well at the same time, right? So that's the concept of space sharing, and this is enabled because there are fairly large server block machines that are out there, right, which can support logins of hundreds of users at the same time who can get onto the machine and do some work, right? This is typically managed by some kind of a professional entity. The server is managed by the IT department of the college, right? So there is some kind of computing services department which will manage the servers. You never get to actually see the physical machines. What you get to do is to log into them and play with the resources the machines actually have, right? So this multiple logins to a server, is it really a cloud? Anybody have any opinion? So you have a server, people log into it, use it. Does it satisfy all the definitions of cloud computing that we wrote earlier? What are the three key parts of the definition? On-demand network access, yeah, we can do that here. on-demand network access. You can log in anytime you want and use it. So shared pool of computing resources. Yeah, the server is the shared pool of computing resources, right? What is the third thing? What is the third part of the definition that we put up? Resources are, it is 4 slides ago, not even 4 slides ago, 3 slides ago. Resources can be rapidly provisioned, precisely provisioned and released automatically. Right? That was the last part of the definition. So precise provisioning. Now when you log in and you have multiple logins to a server, what is the concept of provisioning? What is provisioning? Let's first get to that. Now, if there are 10 users on a server, you can't tell the computer, give one user only so much CPU, and when he reaches that CPU level, stop giving any more resources. Or give the second user only 3 gig out of the 64 gig of RAM there is on this machine, and don't allow the second user's programs to take up more than 3 gig of space. Can you say that? You can't do that on an operating system. You can prioritize processes for CPU, sure you can do that, but that's all vague. A priority of a process doesn't directly translate to a quantitative aspect of how resources are actually handed out to these processes that are running on an operating system, right? So that part of it is a single operating system that all the clients use here, and the boundaries are not very clean. So there are multiple users, the users are there, but if I write a really bad program that takes up 100% of the CPU, then everybody else is going to get starved of CPU on the machine. Yeah? That is likely to happen. Right? Same thing, if I am sending a very, very large file over the network I/O interface of that computer, then others will get starved of network I/O on that computer. If they try to send a file or receive a file, that's going to go much slower than the first person who started sending the file earlier. So that sharing is not very clean. So what we would like to have is something like this, a space sharing model, but with these two downsides fixed, which is I want clean and precise provisioning. I want to create sandboxes in which users can operate, and the size of the sandbox is very fixed. Right? And the second thing is I don't want to restrict every user to be running the same operating system. Maybe one person wants to run Windows, one person wants to run Linux, one person wants to run something else. Right? That's okay to do, and it would be nice to have that flexibility rather than have on a computer on which everybody has to run the same operating system. That's a different concept. Right? So that's what server virtualization does for you. Right? So that those are the cloud computing requirements. Now we'll take a look at a technology that enables some of what we've talked about from a requirements perspective. Then this is called server virtualization. Right? Virtualization is simply the concept of hardware multiplexing. What does that mean? What is multiplexing? Many to one is what multiplexing does. So given a single set of resources, right? Given a single computer, the question is how can you create multiple computers on top of this? Multiple virtual computers on top of this. Right? And that's what virtualization means. It virtualizes the hardware resources and allows these different virtual machines to run on a single host operating system. And each of these virtual machines runs what is called a guest operating system, which can be different from each other. Right? So you could run Linux, different flavor of Linux, Fedora versus Ubuntu, and then you can run Windows and so on. So that's the basic concept of server virtualization. So the nice thing about it is you can have simultaneous execution of more than one operating system at the same time. So each user can run their own operating system of choice. Right? I could be running Windows on the same box as somebody else running Linux at exactly the same time. That would be a really nice feature to have, and that's really what clouds promise you at the end of the day. Right? It has complete isolation of these guest operating systems from each other. In other words, if one of the guest operating systems has a badly written OS and it goes wrong for whatever reason, there's some drastic failure, the blue screen of death in Windows, for example, which comes quite often, it will not affect another guest OS that is running exactly on the same machine. That continues to run uninterrupted, and so any failure in one OS does not affect the failure in another OS. So the OS itself provides a nice clean boundary for them. Right? So there's failure isolation. And I can tell this computer or the host very clearly, don't give more than so many resources to the first guest, don't give more than so many resources to the second guest, and so on and so forth. Right? So that there is a very precise allocation of resources that is possible with server virtualization. Then there are some other nice advantages, such as I can have live migration of these virtual machines. So each one of these guest operating systems is what we call a virtual machine.
Does this host operating system requires to have any special features?
Yeah, I'll come to that. Yes, it does.
To provide this isolation?
Yeah. So it's not the host OS itself, but I'll come to it in a slide. But these are the characteristics of server virtualization. Right? There is a technology that enables this. So the benefits are obvious, right? Suppose we consider that there are two physical machines, PM1 and PM2. Let's say in this case, one is running the computer science website for IIT Bombay, one is running Moodle, which is a course delivery system that we use at IIT Bombay. The characteristics of these systems are that during the day, Moodle is used more heavily during the night than during the day, as it turns out. Because students use Moodle and students are awake at night more than they are during the day. And the website, of course, has more access during the day compared to the night. Right? That's the characteristics of these tools, different kinds of applications that are running on that. Now I could do something like I can have, instead of having two different physical machines, I can have a single physical machine and two different guest operating systems on that, one of which runs the website application, one of which runs the Moodle application. Right? And now I can play with the resource allocations of this. So during the day I can give more resources to CSE or IITB application, and during the night I can give more resources to Moodle. It takes away that resources to give to Moodle from CSE, because nobody is going to access the website past 10 o'clock at night, for example. Right? So now my advantage is that I've gone from two different physical machines to a single physical machine. So I've saved on some hardware. So the hardware is more used for one application during the day and another application at night. Right? So there are also, this is called server consolidation, this concept, and it's a very nice benefit of the virtualization, side benefit of virtualization. So in general, the benefits are that this provisioning can be done very quickly. Right? In less than a few seconds, 30 seconds at most, I can provision a virtual machine to be up and running on some host OS. Right? So that is quickly, and it can be done automatically. There are some nice interfaces that virtualization gives you to be able to do this. Now I can increase the utilization of the server. In this case, I had high utilization of the server 1 during day and low utilization at night. In this case, I had low utilization during the day and high utilization at night. In this case, the server is running 24/7 at high utilization levels, because there is one or the other application taking up the resources. It doesn't matter which one. Right? So what I want is to keep the server running at maximum utilization 7/24. That's my goal. It's like having an airplane. Right? So I can run two different airplanes, each loaded with 50 people, or I can run one big airplane and loaded with 100 people. Because here it has to go to the same destination. You can't send parts of the airplane to different destinations. But the concept is that you don't want to keep an airplane empty. You want to keep it running all the time, and you want to fill the capacity of the airplane as much as possible all the time. Right? That's what the airlines strive for. Same notion in computers. We strive to keep a computer running all the time and it to be used to the maximum capacity all the time. That's the concept. Otherwise it just wastes money. So he asked this question about, is there some special features in the operating system that allows us to do this virtualization? It's not the host OS itself that is modified, but there is a new piece of software or middleware that is introduced between the guest operating systems and the actually the host operating system or hardware. There are different kinds of virtualization, and depending on which one you pick, you can have slightly different diagrams. Okay? So this is called a hypervisor, and the hypervisor plays the role of what we call the virtual machine monitor. So it keeps track of all these virtual machines that sit on top of it, and it allows a translation from the VM OS to the host OS or the hardware, depending on what kind of hypervisor it is. Right? So that's the special piece of software that is needed. Now, of course, there are different open source hypervisors that are available. KVM comes built in with Linux today. So So you don't have to do anything. It's part of the Linux kernel is KVM, right, which stands for kernel virtual machine. And that's open source, and there's another open source hypervisor popularly called Zen, right? And Zen can be downloaded and installed on any box. Many of you may already have done so as well, right, on your laptop. You can even put it on a laptop and have different virtual machines. Now people are building hypervisors for phones, where you can actually make the phone into multiple phones. And why do you want to do that? A use case may be that I am given a single device, however I wish to have an office phone aspect of it and a personal phone aspect of it. I want to keep these two completely separate on the same device, right? I want all my contacts to be separate, all the web pages I browse to be separate, anything that I do with the phone, all the music may be only on the personal device, but I have only a single phone that I carry. Many people today actually carry two phones, an office phone and a personal phone. And a virtualization software on the phone will get rid of this, and you can carry one phone, virtualize it, and you can have two virtual phones. That's what people are building today, right? Okay, so are you all convinced that this is great? If not, then there's no point in discussing. Yeah, so this is good stuff. This is what is powering all of your cloud data centers today in the world. Some kind of virtualization technology. The most popular commercially available virtualization technology is by a company called VMware, which builds a hypervisor called ESX that runs close to 80% of the world's data centers. Right? Microsoft has Hyper-V, which is its own hypervisor. There are many open source hypervisors out there as well. Okay, so flip side, it's all good stuff, but there's clearly some bad stuff that comes with the good stuff. It doesn't come for free, right? So we have basically introduced a layer of indirection. What have we done? We've stuck a hypervisor, which is a middle layer, and that has to actually sort of interpret all the instructions that are meant for the hardware beneath it and send it down to the hardware, right? Because there are different operating systems on top of it. So you imagine a program that is built for Windows using this concept of DLLs and whatever, running on top of Linux, running on top of some hardware, which is what we have, virtualization actually ends up creating. And that's a layer of indirection. And we have solved that, but that usually creates another problem. And this has been the traditional approach in computer science. We introduce levels of indirection, and they create other issues, and it goes on, and that sort of keeps researchers like me in business, because I have something to do all the time. So this is just a joke about, cloud computing and the issues that it has created. But we will take a look in this talk about the actual technical issues that remain to be solved in order to make this really work. Any questions so far? No? Any of it making any sense to you? That's more important, right? Questions will come only if it makes sense. Otherwise, no questions. So we have divided the research problems that we've seen into 4 dimensions of cloud computing research. Right? There may be more dimensions, maybe fewer, whatever. This is a personal opinion more than anything else. The first one lies within the hypervisor itself. So we can take a look deep into the bowels of the hypervisor, and there are certain classes of problems that arise from the fact that there is a hypervisor, there is a guest OS, and so on. And we take a look at those class of problems. The second one is the layer above the hypervisor. Given the fact that you may have a large cloud data center with thousands of machines in it, thousands of physical machines in it, and hundreds of thousands of virtual machines in it, right? Today cloud data centers are minimally of that size. In fact, last week I was visiting a cloud data center by SIFI, which they have constructed in Bombay, and they have not fully built it out, but this is meant to hold something like 200,000 servers, right? 200,000 server machines. Now each physical machine will probably carry 5 to 8 virtual machines. So you're talking of several million virtual machines running in this cloud environment, right? So when you have that scenario and somebody says, okay, give me 100 virtual machines, that's the request that is coming, and each virtual machine needs to have this capacity. Amongst the thousands or hundreds of thousands of physical servers, where do you put these virtual machines? This is a question that can be asked, right? So this has nothing to do with the hypervisor itself, but it's an over and above the hypervisor question. regardless of which hypervisor you are using, this question exists and will have to be asked. So that's the VM provisioning placement kinds of issues that come about that, right? So if I want to move a virtual machine, it's called virtual machine migration, and virtualization actually permits what is called live migration of virtual machines when the application is running on it to another physical host, right? So you can move a VM from host 1 to host 2 even when it is executing. So the questions there would be, which PM will I move it to, which VM will I select to do the migration, so on and so forth. There are many questions that can be asked there as well. So that's one aspect of it. The third aspect would be performance modeling aspects of it. So can I model the performance of applications running on a virtualized environment and predict, what would be the throughput, what would be response times, what would be the resources that would be needed to deliver a certain throughput and response time or some performance requirements, and so on. And finally, we looked at cloud engineering and costing problems. So if I have many cloud providers and if I have many applications to be hosted on a cloud, what's the minimal cost kinds of questions, and where should I place them? What is the placement that will give me the minimal cost out there? Because every cloud provider is going to charge something to give you a virtual machine per hour, per minute, whatever, per day, something like that. So I'll sort of briefly dive into each one of these 4 categories and expose a few problems in there. Obviously, these are not all of them. So within the hypervisor, what are the sources of research problems that can possibly exist? What is the background of people here, by the way? These are all MTech people, GTech people. How many MTech students in here? Yeah, mostly MTech. What is it? Any PhD students in here? Excellent. Okay. So when we looked at the hypervisor architecture and the cloud computing architecture, what we realized was that there is actually more than one control center that is sitting in this architecture, right? Because the host operating system is doing something to manage resources. That's the job of the host at the end of the day, right? What is the job of an operating system? It manages physical resources for you. It provides a translation between your application and the physical hardware that is lying under it. Right? So that is one control center. So when I say it manages physical resources, it has certain algorithms for which it manages memory. For example, memory management is an important aspect of it. It has some algorithms by which it schedules the CPU, and that is also a resource that it controls and manages according to some policies that are built into it. Right? Now what happens is the guest is also an operating system. Right? The guest could be running Windows. Right? And the guest operating system also has some idea of how to manage resources. What it thinks are resources. For it, what it thinks are real resources are actually virtual resources to be managed by the host eventually. Right? Now when there are dual control centers, each one can end up giving possibly conflicting recommendations on how to manage a particular resource. It's possible. Right? And we see cases where that will actually happen. Sometimes they act complementary to each other, but sometimes they actually do redundant optimizations which can actually end up hurting you. Even though each one of them think it's an optimization, they'll end up hurting you in the long run. And I'll go through some of these things. Right? So multiple levels of paging is an example, and I'll show you what that is. Then there may be some inefficiencies in translating between the guest and the host itself. Now that we've introduced this layer, new software layer, will that slow the application down? That's the question that we really want to ask. If so, by how much will it slow the application down? Why is it slowing the application down? Where is the time being spent mostly in this translation?
Sir, is there any embedded OS which support this?
No, not today. It may come. Phone is the closest thing that I can think of that is now having a hypervisor built into it. So Android, there is a hypervisor being built for Android. Essentially, it's an embedded OS to some extent. So what are the sources of inefficiencies in doing the translation and how can we get rid of them? And then of course we can take a look at the virtualization operations themselves. So this is not just doing straightforward execution, but VM migration is something that is specific to a virtualized environment. Right? You don't have to do VM migration, but when it does happen, the hypervisor controls it. right? Can we take a look at processes like this, such as VM migration, and see where the issues lie? So these are the three sources of research problems when we take a look at the hypervisor layer itself. So some specific interesting problems are empirical characterization of Bellur. So what does this mean? I'll come to this, but let me just go through this. So double caching and page cache. How many of you know what an operating system page cache is? You all studied OS in your undergraduate. What's a page cache in an operating system? Somebody back there lifted that.
Any file that is any data that is paged into the memory
Yeah.
be cached for a faster recovery next time.
Yeah. So what happens when you read a page from disk is essentially that the OS tries to cache the page, because a further read of the same page, it just returns it from memory rather than going back to disk. Traditionally, the reason for a page cache has been that disk access on spinning disks is very, very expensive compared to memory access, right? So your memory access latencies are the order of few microseconds, typically, right? Disk access latencies are the order of, speak up, somebody. Microseconds, hundreds of microseconds, thousands of microseconds, hundreds of thousands of microseconds. Actually, it's the last one, right? It's the order of tens of milliseconds, typically, or a few milliseconds to tens of milliseconds. That's where they are. So because of the difference, the OS tries to cache pages as much as it can. Whenever it reads a page from the disk, it shows it into one cache. Now, cache is what? Nothing but memory. So it starts eating up memory as it tries to do this. Now, if there are two operating systems and both try to cache the same page, you're eating up twice the memory for each page that you pick up. Right? So that's an issue. That's what is called double caching in page caches. And you have to ensure now that somebody is not going to cache this page. Right? Now, who is the one that is not going to cache the page? The next question. And so on. So there are some other issues. So that's what we mean by double caching. I'll come back to the first problem in a little bit. Also, in an operating system, there is a single page cache, because the OS is not aware of this concept of virtualization. Typically, the hypervisor manages that, and the hypervisor doesn't manage the page cache. What happens is that the OS has one page cache that it shares amongst all the VMs, right? But if one VM is doing more disk reads than any other VM, basically the page cache will get used up by that one VM, and the effect of caching is now not being seen by the other VMs. That's bad. Right? So you have to give proportionately equal access to the cache to everybody who is out there. And that's what we mean by deterministic page cache allocation. So how do you divide the page cache up itself? And of course more better memory management techniques, understanding all of this stuff. Okay, so that's what page cache management was, but this is what happens in the notion of double caching. Right? So when a VM is running, you would expect that there is a certain amount of free memory that exists out there, right? So the red line is free memory, and the dashed line represents the amount of memory that is being used for the page cache. Right? Now what happens is you expect this to be, because of the way page caching works, this will start going down over a period of time, but not by what we actually saw when we ran our test on this. What we saw was that there is a very rapid degradation of free memory in a virtualized environment as compared to degradation of free memory in a non-virtualized environment. Right? And the page cache starts rapidly growing up, eating most of the memory. Finally, the VM runs out of memory at some point in time, and if you do a memory allocation, you will get an out of memory error, and there are other issues there. Right? There is an unexplained decrease in free memory, even though this VM is actually not reading pages on disk or reading very few pages on disk. The amount of page cache size is disproportionate to the amount of reads that are being done from disk at this point in time. And we know how page caching works. Somebody just explained it out here. So because of this notion, we have double caching that is happening of pages. I already explained this. So the solution would be to actually eliminate one of the caches somewhere. So when a page comes in, just cache it in one place. Right? So either the host or the guest, you either let the guest cache it, because the guest is the one that will ultimately use the page. The application running on the guest is the one that uses the page. It's best that the guest caches it. And this is one solution, but what is the problem with this? Can anybody think of an issue with just letting the guest cache it?
multiple virtual machines.
Yeah, so the moment you have multiple VMs, then you have the same cache page in each of the VM guest operating systems. Right? That also is an issue. Right? What we would like is if there happens to be a shared page, we want it to be cached only once. Right? So we can use page deduplication strategies across the page caches of the VMs. That's one way of doing it, and that's what we've done actually in some work that we've done at IITB. Okay, so that was briefly a look at page caching. So I'm sort of not getting into depth on any of these problems because I don't have the time. I want to cover the breadth of it, and if you are interested, please come and talk to me about depth about any problem. Okay, so what's ballooning? So this is what we want to do. So we talk about ballooning. But what's ballooning? Ballooning is a technology that is used to overcommit resources, particularly memory resources, in a virtualized environment. So let's say we have a 8 gig machine. Okay, there's 8 gigabytes of RAM on this machine. Now I'm going to create 5 virtual machines on top of this physical machine, which has 8 gig of RAM. Each of the VMs is asking for 2 gig of RAM. Right? So in theory, I can looking at the physical resources, I would be tempted to say you can only create 4, because each one is asking for 2 gig. I have 8 gig. I'll create 4. That's the limit, and be done with it. Now the question that you should ask yourself is, when a VM asks for 2 gig, is it likely that it will always be using all the 2 gig? Unlikely, right? So you will ask for it because that may be the peak requirement that you have for something that is going to run. Right, but most of the time it will be, the memory utilization also is a graph. It's not like it's a constant line that is going from left to right for all time, right? And if it's a graph, and if there are multiple VMs, each one of them have a graph of memory utilization over time, it's likely that I can play with this memory. So I can actually create 5 VMs because I know that each VM will not use 2 gig, right? And if a machine needs its entire 2 gig quota, if a VM needs its entire 2 gig quota, I take away memory from another VM temporarily, give it to this VM, let it use it, take it back when it's done, and give it back to the other VM when it needs it. Right? And so on. So that concept is a concept of over provisioning. Right? This is typically what happens on all of your telecom networks, data networks, for example. Right? They will promise everybody a 1 megabit per second connection. Now clearly they don't have enough bandwidth to, if everybody uses 1 megabit per second, you will not get it, I will guarantee this, because no telecom provider is going to have that much of bandwidth. What they depend on is the fact that everybody will not need the 1 Mbps at the same time, right? And that's, they over provision the network. Right? The same concept can be used with memory. Same concept is even used with airlines. In fact, they typically overbook an airplane, knowing that at least 5 to 10% will cancel tickets at the last minute, right? So that concept is the concept of now taking memory away from one VM, giving it temporarily to another VM, let it use it, finish use, take it back and put it back, give it to the next VM when it needs it. That concept is called ballooning. So the balloon is like a flexible thing that exists within the memory space of each of the VMs. So some amount of memory is given to the VMs all the time. Let's say 1 gig I will leave with the VM all the time. I will not touch it. The other gig I play with for this 2 gig scenario that I just talked about. Right? The other gig I keep in a balloon. That balloon may be completely deflated in some VMs which doesn't need the memory at that point in time. And it may be fully inflated in a VM that needs the memory. And then vice versa. Right? So that's the concept of ballooning. It's a pretty cool concept. It allows me to put 5 VMs on a physical machine which otherwise would have probably had only 4. Right? And I want to remember, I want to use this machine to its fullest capacity. And that helps me do that. Right? Particularly in the cases where the CPU is not oversubscribed. Right? So if I have 6 cores, and if each VM is only asking for 1 core, I can give it. I can give all one core to all the machines. It's only memory that is now in demand. And I play the memory by doing ballooning. Now the question is, this is a cool concept, but what's the issue? What are issues that can arise because of ballooning? Any thoughts at all? Suppose I do this. What's going to happen? Yes, that is one. There will be some likely effect on application performance, because when I need the memory, will I have it? Is the question. Right? Maybe the balloon has to be expanded. It is going to take some lag for the balloon to be expanded. So my memory allocation call might take a little longer. Certainly that's one aspect of it. Any other things that you can talk about? You heard of memory fragmentation. How many of you have heard of fragmentation? Anybody who's done operating system class would have heard of fragmentation. On disk it can happen in memory and so on and so forth, right? What I really want is to allocate memory in contiguous chunks as far as possible, right? Because then accessing pages in memory is that much easier, faster and so on and so forth. But with ballooning, because I'm taking memory away and putting memory back and I keep doing this, it can fragment memory in the space, memory space of virtual address space of a particular VM. And that's an issue, right? So fragmentation means slower read latencies or write latencies, access latencies on this. And you don't want that, right? So that's one issue. The other issue is this concept of what are called huge pages. How many of you have heard of huge pages in Linux? No. So what happens is, what is the page size in Linux default? What is the default page size that Linux uses? 4 KB, right? Now with 4 KB page size, there is something called a TLB in Linux. How many of you have heard of the TLB? Sorry to be doing this, but you need to understand terms. Translation look ahead often. TLB, right? What does it do? It maintains a set of memory page addresses to where that actual memory is located. So that also is a little internal translation. It's like a page table, right? For memory pages. And that TLB is implemented in hardware. So it gives you a very fast lookup of where this page is located and you can read it. Now the more addresses that exist in the TLB, the lesser is going to be your memory access time. Right? Your access time will be much faster because you're doing the hardware lookup of the memory page address followed by a read of actual memory. Now, so what Linux does to try to cram as much into the TLB as possible is it creates these, in the background it creates artificially large pages, say 256 MB or some 64 MB. So it takes 4 KB pages, it sticks like thousands of them into one virtual page that it maintains. You don't see this at all, right? And it calls it a huge page and it sticks one entry of the huge page into the TLB. That way the TLB can be used to cover many more pages of the virtual page infrastructure than otherwise, right? Now if I do this ballooning, I can't get huge pages anymore because I'm fragmenting memory. The reason of fragmentation will cause the same problem. Because for huge pages to exist, Linux needs contiguous allocations for a VM, right? And because the contiguous allocation is no longer present, it affects this notion of how many huge pages Linux can actually do. So what the virtualization layer is doing, the virtualization layer is managing the ballooning, remember that, right? And huge pages is being managed by the host operating system, which is Linux. And that's an optimization for Linux. And these two optimizations are clashing with each other essentially. The result of which your TLB misses start going up. Right? If your TLB misses go up, then your memory access time goes up and so on. That's the concept here. Okay? Conceptually that's what's happening. And of course we need to study exactly how much and so on and so forth. So there are a number of issues revolving around how frequently you balloon and its eventual effect on things like TLB, miss ratios, on application performance eventually. All this will come back to bite the application finally in terms of some performance degradation. Okay? Okay, so there are some other hypervisor, those two I sort of just elucidated a little more, but there are many more problems in this space. I'll just sort of list them out, but I won't go into that. So now let's sort of jump above the hypervisor. Let's say in the hypervisor we've solved all the problems, we have perfect hypervisor, so on and so forth. Are there issues above and beyond this? Turns out there are. Right? One is the issue of what my talk was actually going to be about today, which is what is listed in your brochure, which is on the notion of balanced placement. right? The second set of issues revolve around being aware of the concept of power and energy and how to manage it in a computer data center, right? So today this is becoming very, very critical. So if you want to have a eco-friendly data center, then you need to consume the least amount of power, because it turns out that power is also the number one cost of running a data center. Right? The most expensive item of running a cloud data center is power. That's what you pay for the most, not the computers. Right? So power awareness is now becoming a very hot topic of research out there. Many people working in this area. Then this concept of VM migration that I talked about earlier. So cost modeling and prediction. If I have, so the notion of hotspot mitigation is that I have many VMs on many physical machines in a data center. Now one of the physical machines may become a hotspot in the sense that all the VMs are trying to use all their resources, and that is creating some issues. Right? Typically, remember, I have over provisioning. If you have over provisioning and all the VMs are asking for resources, somebody is not going to get resources, and I can't let that happen. So I move or migrate one of the VMs off to another machine, right, live as it's running, so that the other VM can get as many resources as it wants on the new physical machine, and it eases the pressure on resources on the original machine from where it came from. Right, so that is the question now becomes, if I have, let's say, 6 VMs sitting on a physical box, which one do I move? Everybody is putting pressure on resources. Everybody wants all the resources. Right? How do you decide which one to move? Will you move the largest one? Will you move the smallest one? Will you move some random one that you pick? Right? So what is needed there is every VM migration comes at a cost. Right? And if we could understand what that cost is, then we can make a more informed decision about which VM to move off of that physical machine. So that's what this is about, right? And so on and so forth. There are many other problems in the space. So the balance placement problem, I'll just briefly go over this because I was going to talk about this anyway. At least you were promised that I would talk. What is VM? You have all heard of bin packing, right? As a standard problem in computer science. What is bin packing? It's actually not even a CS problem. But what is bin packing? The bin packing problem basically arose out of logistics. So if I have a truck, let's say a FedEx or a UPS or Blue Dart or whatever it is, the courier providers, they all have different trucks, right? And they have many packages to be delivered in those trucks during a day. Now the trick is to figure out how to pack these packages into the trucks so that the smallest number of trucks can be used. Right? There are of course other reasons, other factors driving this, such as the driving distance, amount of fuel used and so on. Let's not worry about all that. Let's say the problem is to simply put packages into these trucks. Now I want to minimize the number of trucks to be used or bins to be used. Right? So the bins have to be packed most efficiently with some set of objects that are going to be put into these bins. Right? And that, it turns out, is an NP-hard problem. So the number of ways by which I can actually do the packing is exponential in the number of bins that have to be packed. Right? Now, so VM placement is very similar to bin packing, because I have a number of VMs, right? And I have some n VMs. Each VM is of some size. VM1 may be of 2 cores and 2 gigahertz, 2 gigabytes. VM2 may be 1 core and 3 gigabytes, and so on and so forth. Right? Each one has a size in multiple dimensions, and I have to now pack these VMs onto physical machines so that they all fit, and I minimize the number of physical machines that are eventually going to be used. Why do I want to do that? Because of power considerations. I want to run minimally the number of physical machines that are possible. I shut down every other physical machine that's there in the data center, and then therefore I can save power. Right? So that is bin packing, and that's what we always thought is a good idea to do. But the goal has been so far to pack these VMs as tightly as possible into these bins. Right? So cram the physical machine to the extent possible that all its resources are fully used up, and then move to the next physical machine, cram it as tightly as possible, and keep going. And that will obviously minimize the number of bins or number of physical machines used. right? But is this the best way of doing things? Now, in a package situation, right, when you're actually packing trucks or boxes with objects are of fixed size. Now the package won't change the dimensions as the truck is driving, right? The package is nothing but a cardboard box of some kind. The dimensions are fixed on the cardboard box. The height, width and length are fixed. So once you pack it, the packing will stay as you have packed it. There's no issue, right? But if the objects were changing size as the truck was moving, then this packing would fall apart very quickly, right? So that is the concept even here. The VM actually is not like a object to be packed, it turns out. Because the VM changes its requirements as time goes by. The amount of CPU is never fixed, it's not a straight line, the amount of memory is not a straight line, the amount of IO is not a straight line. They're all graphs that look like this. They go up and down. It uses more sometimes, it uses less sometimes, because that's the way applications are. That's the way workloads are, right? If you run a website, you won't have a constant number of hits every second. It is impossible to have. You will have more hits at some points of time in the day, you will have less hits at some points of time in the day, and that's the way it will go. So, the trade-off then for us is that, so how do we deal with this? We can deal with this in a very simple way. I take the peak requirement of any VM and I provision for that. I assume that's the size of the VM, taking the peak requirement. So if I say it's 82% CPU, I'll provision that VM for 82% of a core. But then, when it's not using 82%, I'm wasting CPU at that point. That's it. I just let it go. That's also somewhat foolish. Then my tightness of packing is gone for a toss because I'm provisioning it for the peak. Right? And I do this on all the resources. So my traditional trade-off is actually between how tightly can I pack it versus how much room for growth can I give to it. Right? And that's an interesting trade-off. So if you have very tight packing, then you have very low stability. Because if a VM now needs to expand, it has to migrate. That's the only choice that it has under tight packing situations. And migration is expensive. Right? The other end of the table is that it's very, very stable because I've provisioned it for the peak, but my tightness really sucks. I'm using many more physical machines than is required in order to run these peaks, and so on. So the question is, where along this curve do you want to be and how do you get there? That's an interesting research problem in itself. Right? So the power problem, how much time do I have? Who is monitoring my time? I'm not.
Okay.
10 minutes. Good. So the power problem is early processors. Basically, there are two components of power that is consumed by a computer. One is called idle power. One is called peak power. Idle power is the power that is consumed by a computer when its CPU is at 0% utilization. It's theoretically never at 0%, but no applications are running, only the OS is running, right? The OS is running, and typically there's some level of power consumption that is happening when it is idle. And peak power is power when the CPU is being run at 100% utilization. So you run some program that continuously takes up CPU, and so early processors, right? If you take the Pentium, dual core, and all of those processors had peak and idle power be roughly the same. They really didn't have any differentiation between them. That's the way the processors were designed and they worked. But if you take a look at the latest machines, the Intel i7 for example, which is one of the latest processors in their range, you notice that the idle power sits at around 30 watts or so. 30-32 watts is what it consumes during idle, right? But the peak power varies widely between what frequency you run the CPU at and how much of the CPU is being used. So let's say it ran at the peak frequency of 3.4 gigahertz. That's the peak on the i7 that you can run it at, right? 3.4 gigahertz. So if you ran it at 3.4 gigahertz, there is a red line, right? So you see that at full capacity, when you're running it at 100% CPU, you're running roughly at about 80-82 watts in that range, right? And this is assuming you're going to run it at the frequency of 3.4 gigahertz. But now there is also a very interesting capability that is given by modern processors. I can cut the frequency and run it at a lower frequency. And you can do that with earlier processors. So earlier processors did not have the capability to run a 3.4 GHz processor at 1.6 GHz. But I can now do that. Right? I can take the i7 and say run it at 1.6 GHz and it will do that. Right? Now at 1.6 GHz, this is a variation between ideal and peak. So there are two dimensions along which you can control power now. Right? One dimension which is always there, which is the amount of CPU that is being used. Right? And that actually controls power because there is a significant variation of what we call the dynamic power range of a processor. The dynamic power range being the difference between the ideal and peak power at any frequency. Doesn't matter. Right? The second dimension is the frequency dimension. If I don't need a program to be running the processor at 3.4 GHz, why would I want to do that? I'll step the frequency down, run it at a lower frequency, consume a lower power and still get my work accomplished. I can do that potentially. Right? So given those two controls, it's called DBFS, those controls, can I play with them in order to do provision? Is the question that we ask ourselves. Right? So that's what is out here. So the modern processors offer these dynamic voltage and frequency scaling knobs. Let's not worry about voltage at this point. Voltage is also coming soon because you always thought your processor ran at 5 volts, but it doesn't. It turns out you can run it at different voltages. But not even going there, just playing with the amount of CPU and the frequency, you get so much variation in power. Right? And if I have that variation, can I exploit that variation to run my application so that you meet the SLAs of the application and yet consume the least amount of power that is possible to be consumed? That's the question. Right? That's the research question at hand. So that's the balance you are playing with is performance and power. Right? I can always run the program at 100% CPU at the highest frequency and it will consume some amount of power. The question is if you don't need to do that. So suppose you're running MapReduce as an application. You run all the map tasks at really high this thing, but the reduce tasks will have to wait because all the map tasks have to complete because before the reduce runs. What is the point? I might as well run the map tasks a little slower, some of them a little slower, so that all of them finish at the same time. Right? That's the concept that we are playing with at this point. So the goal is to basically provision VMs that satisfies that basically looks for the best point in the trade-off between power and performance. And we can ask many questions here. You can say, of course, the eventual interest is not that of power but of energy. Right? Power over time is energy. Eventually, right? Is the amount of energy consumed, amount of watt hours consumed is what you're really going to pay for at the end of the day. Right? So if I can run the program a little slower, satisfy its completion time or SLA requirement, and yet consume the lowest power, that's what I want to be able to do.
Typically, how would we charter the SLA part terms, the performance part?
SLA is response time. That's what we are looking at as. So you want to meet the response time requirement and yet minimize the power consumption.
If I submit a job to a data set,
Yeah.
saying that this should be done by this time,
Yeah.
and it should be running at the lower cost.
Yeah.
It's not. I use only CPU. And then from the other side, from the data center side, the provisioning engine side, they're looking at how much of power is being used.
Yes.
For this to be configured. The least possible is the best.
Yes.
So how should we define this in our job? When I submit a job as a user,
You will not worry about the power as a user. What you worry about is you will specify your response time, completion time of your job. So you say this job needs to complete in 43 seconds. Right? The data center provider will say, okay, to complete this in 43 seconds, how much CPU, what is the frequency I need to run it at? That's the question they have to answer. You don't have to answer that as a user.
at the moment the Amazon EC2 and things like
Well,
that.
this is all still in research. I mean, this is not production stuff. This is a research problem at this point. They don't know how to deal with it yet. Right? But it's coming. I mean, sooner or later it will come. Okay, so I think largely I'll stop here. There's a lot more stuff, but don't think I have the time to do this at this point, and so I'll open it up for questions rather than. Yes.
In the case of overcommitment, whether the resource utilization history will help in the selection of correct VMs?
Yeah, absolutely. Right, so the more historical data you have, the better you can drive the overcommitment provisioning decisions. No question about it. Right, in fact, almost all provisioning is done with some time series behind it. Nobody does provisioning without some amount of historical data. Right, and this can be dynamic, this can be static. You can also place provisioning can be even done dynamically or re-provisioned dynamically. As the VM is running, you can say change the amount of max CPU it can use. You don't need to bring it down to do that. So, the more data you collect, and as you move on, you're collecting data all the time because you're monitoring it, you can fine tune these decisions along the way.
So I could see that you were making the entire presentation was based on assumption of post verification and your guest was running on top of the host. I was wondering why you were not very keen on touching upon bare metal virtualizations.
No, I am. So those, it's not all the problems are applicable to all kinds of virtualization. So let me state that. It's pretty clear, right? So problems of these dual control centers don't necessarily apply to bare metal virtualization, like VMware does, for example. So ESX is a different beast, but KVM is also picking up usage, and KVM does suffer from some of these issues. So yeah, that's true. But many of the other issues, it's not the entire presentation, all the issues on top of the hypervisor still apply even to VMware uniformly, and so does power considerations. All of them still apply to VMware because they don't have anything to do with the way the hypervisor is architected. I didn't want to get into details about bare metal versus para-virtualized versus that stuff in this audit, but sure, absolutely. Any other questions?
Hardware being used for this kind of research? So in-house?
We have a small cloud that we have built at IIT Bombay that we are using. This is all these problems, by the way, are problems we are working on in our ProVM research group. The hardware is about 200 cores, so they're all 8-core machines. So about 25 to 30 such machines. So 2 Xeon CPUs on each one of them, which have DVFS control. So there's one PhD student, Shweta, who's working only on power. There's another PhD student working on power for Hadoop or MapReduce environments only. So Hadoop scheduling for power optimization. The way that you schedule jobs also matters in terms of power. So she's looking at that. But that's the hardware setup. It's a small research cloud which has about 200 cores.
Yeah, when I ask this question, I try to compare this with a knapsack.
WinPack, yeah. Oh, for that we have simulators, which test much larger.
That's problem than the line problem in the sense that you have racks and you need to know how you move across the racks and between the racks. It's another more complex problem.
Yeah. So the practical version of this will have to take that into consideration as well. Now, of course, first you have to solve the theoretical problem, which is what we are trying to do. But ultimately, when you apply it, you may have to divide or subdivide the problem before you end up applying it the way we do, which is, like you rightly said. So given some set of VMs belonging to an application, maybe there are some constraints on, across racks versus within a rack placement and things like that. And those can be modeled as constraints even in WinPack. So you can say I'm going to divide my bins into these groups, and then there are some additional constraints saying 2 VMs belonging to this must belong to the same group. I can model it in that way. But then it sort of no longer becomes a traditional WinPacking. It sort of starts varying.
You use some simulators like CloudSim.
We used to do some work on CloudSim that we have now stopped for no reason other than we don't have students to work on. But otherwise we have other simulators as well that we have developed for testing displacement particularly, and that's our own simulator.
So that's within the box.
That's within the
So what kind of software tool you are using in the sense of software like virtualization?
What hypervisors are all open source. Right now we are only working on Zen and KVM.
Middlewares?
No middleware. Testing applications is Rubis, which is e-commerce 3-tier middleware application. That's just for testing purposes because you can vary loads and stuff like that. You can vary the size of the database and so on. So Rubis along with a whole bunch of benchmarks, LinPack, NASA parallel benchmarks, those kinds of.
Because you are telling a model that when two VMs are running in a particular machine, depends upon the usage, you can scale up, scale down and all these things.
Yeah.
So who manages this kind of things?
Who manages this then?
In the sense like VM, somebody should know, right? Some component knows that, okay, this VM has to scale up or scale down.
So the hypervisor typically manages that. So the overcommitment concept is that you ask for some amount of resources that you feel you need as a VM. Now you may not use all the resources, the hypervisor may not give it to you, but you don't know that. You ask for it anyway, and when you need it, it will come to you. That's the hope. There is nobody who needs to manage it. The hypervisor will manage it.
So in our state, the electricity is state. That means the cost of the electricity, the power is differ from time to time and place to place.
Yeah.
When the peak hours, the electricity is goes before us.
Yes.
Can we automatically shift our machines idle here and take our jobs executing someone?
It's an excellent problem. So, in fact, we studied one problem which has a two-part data center. One is running on solar, one is running on grid power. Okay, so one of the problems in that setting is that when the grid power goes off, let's say, right? Don't even take solar, just take two data centers on grid power. But one place has unstable power. When the power goes off, the UPS backup is some X minutes. Let's say 30 minutes or an hour is your UPS backup. Now the interesting problem there is that given all the VMs that are running on the data center, I want to migrate all of them to the more stable data center, right? It may have more expensive power, but I need to migrate it there for now, but within a certain fixed time, which is when my UPS is going to go. So I have 30 minutes, I want to migrate 27 VMs, can I do it, is the question. And if I can do it, what is the schedule that permits me to do it? The schedule, the order of VM migrations actually matters in this case. Very interesting problem, we are looking at that problem, for example. This is also an interesting one. So as the power budget changes,
will it give a good feel that it is no shifting is taking place?
I'm sorry, I don't hear the question. Can you repeat it?
So will it give the good feel that there is no such changes are happening?
Yeah, that's the idea, that you don't want users to know any of this stuff. You have to have policies and agents that enforce these policies, software agents that enforce these policies in the background, such that the user doesn't even know this. That's the eventual idea. Sure.
How these concepts work in software as a service? Here actually you are talking about computing resources.
Yeah, so this is all problems that are close to the computing resources themselves. Problems may not be directly applicable to software as a service, but there may be other issues. I mean, so some of the questions that we've asked is software engineering for the cloud any different from software engineering for non-cloud environments? Is the process itself, does it need to be different? That question is something we have considered. But provisioning for software as a service certainly is an issue. That you have to say, you can ask the same question in terms of app server threads, for example. Now, how many threads or how many database connections do I need from an app server? Can that be over provisioned? How will that be managed? I can think about some of them. I haven't given it enough thought to answer the question authoritatively.
So what changes are needed from our side while developing a software application to make it cloud compatible?
That's a different topic. Maybe I'll take that question offline if you don't mind, because it's not directly related to this response. But I'll answer to the best of my ability offline.
Sir, any questions? Over your years of experience, how do you find the trend in the interest of the students towards research? So many companies opening up job opportunities.
So our own BTechs, if we take a look at the BTech profile from IIT Bombay CS, that is changing. From let's say from 2003 onwards or 2004, last 10 years, 2004 to 2007 or so, it was completely targeted towards MBAs and jobs in the financial industry, because they were very high-paying jobs, and so people would mostly take up those jobs first and then go to an MBA at NIM or something like that. That was the trend. And about 2008-9 onwards, it shifted to taking jobs in tech companies at least. At least they weren't going to finance companies or banks. They were taking jobs in tech companies, Facebook, Google, those companies started hiring, and then so many went to jobs there. Over the last 2 to 3 years, the trend has again changed, where more than 60-65% of the class is now writing GRE. So they are at least going for grad studies. Certainly won't be in India, but at least they are going for grad studies, which is a good sign, in my opinion. So that's been the trends of BTech people. Tendency towards research, I think even from a PhD program perspective, our group, at least our research group, is seeing far better applicants now than we used to see 7-8 years ago. Right? So this recent, the PhD admissions are concluded in June. So the May-June hiring period saw 12 PhDs join, out of which 4 were from Indian Institute of Science, masters. And 2 people or 1 person was from ISI in Kolkata. So that's a good profile. We never saw that profile earlier. So I am more encouraged now than I was 5-6 years ago. Any other questions? Okay. Thank you very much. I'll take that one question offline. That question. What was the question? If you have a minute, I'll try to answer it here.
In the software side, what we have to take what additional care we have to take while developing applications to make it.
Yeah. So that was the question. So couple of things. One is testing for cloud environments is different from testing for non-cloud, because the testing processes have traditionally always assumed your resources to be stable. You never test with varying resources, right? You never test with ballooning as a condition. You never test with 10 VMs being placed on the same machine as a condition. So that testing process is certainly something that you have to look into carefully. I'm not saying it's going to be entirely different, but there is an impact on testing, which is serious. Development, I'm not so sure it's going to be very different. The requirement side of it also is going to be somewhat different, because if you're so again you have to ask the question, are you developing software to be run on the cloud, or are you developing software as a service? Those are 2 different questions, right? Which also runs on the cloud, but it is being exposed as a service now to a different set of people, right? So software that runs on the cloud is only impacted, I think testing is the biggest impact there. The software as a service, there are a whole number of impacts. Requirements, architecture, all of them are impacted because your variability there has to now be taken into account. Right? So in other words, I should be able to accommodate customers with slightly different needs, all at the same time. In other words, the customizability angle suddenly becomes very important. You have to build customizability into the software right at the beginning. You can't add it ad hoc later. It's much more difficult to do that. So from a customizability perspective, requirements, design, architecture, everything will get impacted. And still, since it runs on the cloud, your testing will get impacted. So So there's a much more major impact of software as a service as opposed to just software that runs in the cloud. It's not being offered as a service, but say it's a single company software. That's also okay. But their testing, I think, is a big impact.
Sir, I will come with an example of this session.
Sure. No problem.
Spend some time.
Yeah, I am around as long as I have another talk to give at another college somewhere here. But I don't know what time that is. But I'll be around. Okay, if there are no other questions, thank you very much for staying patient.